In the previous video, we have discussed the IV behavior of a single solar cell, an ideal PV module, and a non-ideal PV module. We will now continue our discussion of the IV curve of interconnected cells. In particular, let's look at the series connection between two solar cells. Ideally, the two cells have the same voltage and current. In the equivalent circuit, the cell is represented by means of a current generator and a diode placed in parallel. The solar cells can consequently be included in a larger circuit and more easily analyzed. In case both cells are subjected to the same irradiance, they will, in the ideal case, deliver the same amount of current. Therefore, the ideal IV characteristic of cell 1 overlaps with that of cell 2, highlighted in blue. What happens when we connect both cells in series and place a load in the circuit? We can see that the current flowing through cell 1 and cell 2 is the same, while the voltages add up. So a module with the two connected series cells will deliver, with respect to a single cell, the same amount of current and twice the voltage. In reality, however, it might happen that the cells have a voltage mismatch, perhaps due to slight variation in the fabrication process. Here, this difference in open circuit voltage is exaggerated to be graphically visible, but realistically the difference can be in the range of 10 to 20 millivolts, so around 10 times smaller than depicted here. The IV characteristic of the series connected and the voltage mismatched solar cells is shown here. The current remains the same, while the overall voltage is again the sum of the two cell voltages. The effects are more severe when considering a mismatch in the short circuit current of the series connected solar cells. This can occur, for example, in case of partial shading of cell 2. In this circumstance, the cell 2 current is lowered with respect to that of cell 1. This represents the bottleneck of the series connection. The current through the two cells must be the same. Therefore, the total current cannot exceed that of the cell with the lowest current. Basically, the current difference between cell 1 and cell 2 is forced to go through the diode of the good cell 1. Looking at the balance of voltages in this net, cell 1 will be forward biased, and since the low current cell number 2 is directly connected to the good cell 1, cell 2 becomes counterpolarized and therefore experiences inverse voltage. This means that the cell starts to dissipate power in the form of heat. The power dissipated in cell 2 can be graphically determined with the following approach. You start with the IV curves of both single cells. We then take the IV curve of the good cell 1 and mirror it with respect to the current axis. The intersection between the two IV curves is the operating point. The operating point is now located in the top left quadrant, where the cell 2 has a reverse bias. Therefore, the highlighted red area here is the power dissipated as heat in cell number 2. You can imagine that when this happens for a few seconds for the two cells we are just discussing here, there are not that dramatic consequences. However, now imagine a string of 10 cells where 9 of them are unshaded and functioning well, but a single cell is shaded. This can be because of a leaf, due to bird droppings, or even due to a chimney. The excess power of the 9 cells will be dissipated in the only one shaded cell, and this now has important implications because the shaded cell can easily break if it becomes too hot. What about when we connect two current mismatched solar cells in parallel? In the ideal case, we have two solar cells with the same voltage. We then know that with respect to a single cell, the total VOC of the combined cells will be the same, while the total current is equal to the sum of currents from both cells. For the parallel connection, it does not matter whether one of the two cells is mismatched from the illumination point of view. The only important thing is that the voltages are similar. In case of two parallel connected cells with a voltage mismatch, the currents of the individual cells are still summed. The combined VOC, however, is now somewhere in between that of VOC1 and VOC2. Again, you can find the combined voltage by means of a graphical approach in which the IV curve of cell 1 is mirrored with respect to the voltage axis. So, to conclude this video, we have discussed the external parameters of a single solar cell and introduced the equation for the IV characteristic of an ideal module. We then investigated the IV behavior of two ideal and two mismatched series or parallel interconnected solar cells. In the next video, we will learn how to prevent the power loss in interconnected mismatched solar cells through the use of bypass and blocking diodes.